So in the previous clip, I showed you how to compute the determinant of this 3 by 3 by expanding by cofactors. There's a shortcut that you can take, and this is for 3 by 3 matrices only. But it's a handy little shortcut that you can take, and it goes like this. So we'll take the same determinant, 2, 1, 2, negative 4, 3, 1, 1, 0, 4. And what I'll do is I'm going to take these first two columns, and I'm going to make a little dummy copy of them over here. I'll make it slightly light colored so that you can see that it doesn't super matter what's going on here. And then what you do is you take products going down the diagonals. So coming down here, we have 2 times 3 times 4, so that's 24. And then we have 1 times 1 times 1, so that's 1. And then we have some stuff times 0, so that's going to be 0. So I'm going to have a plus 24, a plus 1, and a plus 0. Then we look at the other diagonals, and coming up this way, I have 1 times 3 times 2, which is a 6. And then I have some stuff times a 0, which is a 0. And then I have 4 times minus 4, so that's minus 16. So I'm going to subtract these ones. So these ones come with a minus sign. So I have minus 6 minus 0 minus negative 16. Okay, and so then that gives me 25 plus 10, so I get 35 again. Okay, so let's see. So another observation from this computation then is that if A has a row of zeros, then the determinant of A has to be equal to 0. So you can see that by cofactor expansion down a particular row, or by noticing that, well, at least in the 3 by 3 case, if you do this zip, 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 zap, zap, zap method with the diagonals, you're going to pick up a 0 in each case. However, I should emphasize again that this shortcut here is only for 3 by 3 matrices. Don't ever try it for a 4 by 4 or bigger. It will not work. So another thing that we can see from cofactors is this theorem that we had before about how if A is triangular, then the determinant is just the product of the diagonal entries. Okay, and so to see that, you just take the determinant of an upper triangular matrix using cofactor expansion. So let's just do it by example. So this is like not really a proof, but you'll be able to see that what happens for this example happens generally. So I'm going to take a generic 4 by 4 matrix. 4 will be good enough to amply get the point across. Okay, so we're going to compute this determinant here, and I'm not writing in these entries down below. These are all zeros underneath the diagonal down here because it's an upper triangular matrix. Okay, so we are going to compute this determinant, and you say, okay, let's do it by cofactors. Let's expand along a likely row or column, and then immediately the laziness principle suggests let's take the one with the most zeros. So we'll expand down this guy. And since there's only one non-zero entry in that column, we're going to get exactly one subdeterminant, the one obtained by crossing off that row and column. So we have A11 times the sign is going to be positive 1 because we're in the first row, first corner. And then we cross off the row and column, and we have A22, A23, A24, A33, A34, A44. So we have this one, and then, like I said, the other ones here, these zeros right here are going to make sure that nothing else comes from this particular expansion. Okay, so then we can do another expansion, and it looked like doing that first row worked pretty well. So now we do this one, and now A22 is in the 1, 1 slot, so it comes with a positive sign. So we have A22, positive 1, and then we cross out the row and column for the A22 entry, and we get the subdeterminant of A33, A34, 0, A44, and this gives us the formula, at least in the 4-4 case. And so it always boils down just like that. You can expand down the first column, or in the case of a lower triangular matrix, you can expand along the first row, and it will just work out exactly like this. The one last implication to see from this cofactors technique is something we haven't discussed before, and that is that the determinant of A transpose is equal to the determinant of A. And I'm not going to go through the details, but the general idea for this is that expanding along the ith row of the transpose leads you to exactly the same computations and the same numerical values as expanding down the ith column of A, because the ith column of A is the ith row of A transpose, because transposition swaps rows for columns.